Hello friends, welcome to the online lecture series of St. Andrews Institute of Technology and Management in Gurugram. My name is Saitm and I am an assistant professor in Etce department in Saitm. So our today's topic of the lecture is Ring and Johnson counters, which is a part of Unit 3 in Digital Electronics. So in last lecture we learned about shift registers, which is a combination of flip-flops to store more than 1 bits at a time. So now let's see some of the applications of shift registers. What can be the applications? So shift registers can be used to store data temporarily. If I want to store 5 bits of data, I would need 5 flip-flops. It can be used for multiplication and divisions. Okay, it is used to divide the clock frequencies in timer circuit as well. It can be used as a delay line, okay, or serial to parallel and parallel to serial data converter. It can be used as a ring counter and twisted ring counter, that is called Johnson counter. So today we will see a ring counter and Johnson counter in our lecture. So let's first start with the ring counter. So ring counter is a special type of application of a shift register. There is only a little bit of change in the design or the diagram of the shift register or in a ring counter. That is, it is nothing but a shift register, but the output of the last flip-flop, as we can see in the picture, the output of last flip-flop is fed to the first flip-flop. That is, we have created a ring over there, and the output of first is fed to the input of second, output of second is fed to the input of third, and output of third is fed to the input of third, and output of fourth one is feeding once again to the input of first flip-flop. We have applied the same clock, that is the synchronous one, to all the flip-flops simultaneously. Okay, so this is the construction how we can build a ring counter. So counter is basically used to count some sequence. So let's see how this ring counter will count. So we are considering negative edge triggering of clock, as we have seen in the shift registers as well. Okay, so the intermediate output, as I have already told you, are connected to the input of the next flip-flop. So intermediate outputs, that is, these are the ones which are connected to the inputs of the next flip-flop. Okay, let's see the operations now. Initially, let the 0 is stored in all the register, or we can say in the shift register, or all the flip-flops. That is, initially what we have 0 0 0 and 0. On first negative edge of clock, as we apply d naught is equal to 1, so q naught will become 1 as we are using the d flip-flop, and as the data will be equal to the output in a flip-flop. So if I apply 1, it will get stored in the first flip-flop, that is 1, and its output would be 1, and all the other ones are 0, so it becomes 1 triple 0. Okay, so q naught has become 1, Q0 has become 1, others are 0, 0 and 0. Now as it is a shift register whose last output is fed to the input of first flip flop. Now at the next edge what would happen? This one would transfer or transition to second flip flop, so it and this output goes into the input, so it will become 0 1 0 0. On the next edge this 0, that is this will go and come in the first flip flop, and this one will move over there, so it will become 0 0 1 0. And on the next edge we can also see it would become 0 0 0 1. And if I apply another edge, negative edge pulse, then it will become 0 0 0 and 1 would come again into the, so it will again become 1 0 0 0. So this is how a ring counter works. As we can see here, the Q0 becomes 1, and if I convert it into binary 0001, it would become, this is our LSB, we are fitting the LSB first, so this is our BMB, it will become 1 0 0 1 0. It is represented in binary. If I will convert into decimal, it will be 2 0 1 0 0 would be 4. Okay, similarly 1 0 0 0 would be 8. So this is how a ring counter would count, that is from 1 to 2 to 4 and 4 to 8, because we have only 4 flip flops, so that is up to 8 is possible. Okay, so this is how it will work. I have explained it in the steps as well. So first it will become 0 0 1 0, then it will become 0 1 0 0, then it will become 1 0 0, and it will again become 0 0 1. So it will move on rotating like this, 1 2 4 8, then again 1. So that is why it is called a ring counter. Okay, so number of output states for a ring counter will always be equal to the number of flip flops, that is the number of flip flops we are using to design the ring counters. So the ring counter can also be constructed by using JK flip flop. As we have seen, it is constructed using D flip flop, so we can also construct it using the J flip flop, that is JK flip flop, and this is how it will look like. The output of the last flip flop Q2 is fed to the input of first flip flop. Okay, and this Q2 bar is fed to the second input K0. As we all know, JK flip flop has two inputs, J and K. Okay, and the same operation can be performed on this JK flip flop also. So now the next is Johnson or twisted ring counter. So it is similar to ring counter, but the difference is in the designing only. Look here, here we have fed the first input. As we have seen, the output should be fed to the input of the first flip flop. Here instead of Q3, I have fed Q3 bar, complement of Q3 to J0 and the Q3 to K0. So this is the only difference between a ring counter and the twisted ring counter. The complemented output is fed to the first flip-flop at the J0 input, and the uncomplemented one is fed it to the second input K0. So this is how the construction would look like. It will consist of 4 flip-flops, okay, in this format as I have drawn here. 4 flip-flops are connected in this pattern. So this is the twisted ring counter. In university exams it often comes, what is the difference between a twisted ring counter and a ring counter. Sometimes they give us this question only, that explain Johnson counter. So we should know that Johnson counter is nothing but a twisted ring counter, okay. So this is the construction. All the flip-flops are negative edge triggered, as we have already seen what is negative edge, and clock pulse is applied to all of them simultaneously. All the flip-flops are applied the clock pulse simultaneously, okay. So initially all of them have zeros, so it will be 0 0 0, okay. Now initially Q3 is 0, as all of them have 0 stored in them. So initially Q3 is 0 and Q3 bar is 1. So this Q3 will go to the input J0, okay. Q3 bar, that is 1, will go to the Q3 bar will go to the J0, okay, and 0, Q3 is 0, it will go to K0. So what would happen? As we can see, Q3 bar will go to J0 and J0 will become 1 and K0 would be 0. So on first falling edge of our pulse, what would happen? The first flip-flop, that is FF0, will set, because the output input is Z0 is equal to 1, and we all know the truth table of JK flip-flop. It will be set if I provide J is equal to 1 and K is equal to 0. So Q0 will become 1, okay. So the first flip-flop will set and Q0 will become 1, and output of all other flip-flop will remain unchanged. So it will become 1 0 0 0, or as we are, because it is the LSB, I will write it over there. It is Q0, Q1, Q2, Q3. So LSB will be written over there, 1 0 0 0. Now as we have got the 1 at Q1, okay. So at Q0 is 1. Now on the second negative edge, what would happen? On the second edge, Q3 bar is 1, will be equal to J0 is equal to 1, and this will set the flip-flop. FF0 will set Q0 1 will become input to J1, and J1 will become 1 and K1 will become 0. So on the second edge, what would happen? On the first edge, flip-flop 1 was set, and now the flip-flop second will be set, and Q1, as on the first negative edge, Q0 was becoming 1, and now Q1 will become 1. So what we would get? 1 1 0 0. On the next stage, what would happen? 1 1 1 0. On the last fourth negative edge, what would happen? 1 1 1 and 1. So this is how it will work, okay. On the fifth falling edge, what would happen? On the fifth falling edge, as Q3 is 1, it will be fed to K0, and Q3 is 0, so J0 would be 0. These two inputs would be fed, and what would become in the last? All the flip-flops will store 1 1 1. That is in, it is in represented in binary, and decimal equivalent of it would be 1 2 4 8. 8 plus 4 plus 2 plus 1, that is, it would be 15. Okay, so this is how it will be. The Johnson or twisted ring counter will count. So here we can see it will count like this, 0 to 1, because initially all of the flip-flops were containing 0. On the first negative edge it becomes 0 0 0 1, that is 1. On the second edge it becomes 3, because two flip-flops will get ones. On the third negative edge, three flip-flops will get 1 1 1, and it becomes 7. So similarly it goes on like this, 0 1, then 3 0 0 0 0, then 0 0 0 1, then 0 0 1 1, then it becomes 7, that is 0 1 1 1, then it becomes 15, that is 1 1 1 and 1. On the next stage it will become 14, that is, this will become 1 1 1 and 0. Okay, now if we continue, it will then become, after 14, 14 is 1 1 1 0, then it will become 12, that is 1 1 0 0. Then after that it will become 8, that is 1 0 0 0, and again in the last it will become 0. So this is how a twisted ring counter will work. And here is the timing diagram of the clock. At every negative edge, as you can see, the one flip-flop will set. At first, as we can see in the picture, at first negative edge, here at first negative edge the Q0 is set. At second negative edge, Q1 is set. At third, the third flip-flop, and this is how a Johnson or twisted ring counter works. So this is all about the ring counter and twisted ring counters. In the next lecture we will see synchronous counters and asynchronous counters. Thank you very much.